Hi, this is a brief introduction to KNN or instance-based classification methods because I simply want to give you a very short overview on what is this method about. The goals for this week will be to understand how KNN works and from that point to implement our own version of KNN in order to fully understand what is the mechanism behind. And on top of that, to learn how to use the different metrics that are involved in the mechanisms that KNN uses to work with a classification task. By mid of the week, I will try to introduce this second topic on KDE, kernel density estimators, which is a family of classifiers which is very much related to KNN. But for the moment, just try to feel comfortable with KNN. So besides this short introduction, I will upload a very short overview on how to work with KNN, and we will just start working with examples on KNN that are already available in GitHub and that I will upload afterwards. So let's start. So KNN is here, okay? It's a classifier as you know it, but it's based on the geometric or the distance information contained in the dataset you are working with. Okay, so if you think about trees, for example, they are not working with distances between the samples or the instances in your dataset. It's simply working with how the different features split the dataset into suitable categories that are serving for the purposes of your classification task. There is another family of probabilistic or non-deterministic classifiers, which is the Bayes classification family, from which we will cover linear and quadratic discriminant analysis, and we will also cover naive Bayes, for example, for text problems. Regression is out of the scope here, because you know what is regression. It's not a classification family. And the final set of classifiers that we will cover are support vector machines. So for the moment, focus on KNN because it's a quite powerful method. And it's important that I will remember you that KNN has nothing to do with k-means, okay? Some of you might consider that k-means is something related to KNN, but has nothing to do with that, okay? K-means is a clustering technique, is not a classifier, it's unsupervised, and KNN is nearest neighbor classifier method that we will see. So instance-based classification family of classifiers represented here by KNN and kernel machines at the end of the week are based on the idea that they will classify elements based on the elements that surround that element. So I will classify a new event based on the information provided by the events already in the training set that are close to it or that are most similar to that new instance that I want to classify. That is the basic idea, right? So the whole point is to define what do we consider what is most similar in this case, right? For that, we will have to define what is a distance or what is similarity between two events or between two samples or, if you want, between two rows in a data frame. So in order to classify, what we do is to find what are the most similar events close to that and to use what is the most frequent label or class among these k neighbors in that dataset. And once that you find those elements that are very similar to the one that you want to classify, what you add is what is the majority of labels present in that subset of elements very similar to the one you want to classify. And at that point, what you do is to simply set the label based on what is the weighted majority or the most voted majority, or you name it. There are thousands of schemes to be used in order to determine what is the label to be assigned to that element that are very close to the one you want to classify. Let's see an example. Here we want to distinguish between the minus and the pluses, the classes, okay? And we want to classify this guy here, right, the x. So if we consider only one neighbor in the KNN family, k is a parameter. Remember that k is a parameter that we have to specify. So if k equals 1, we will find what is the one nearest neighbor to my element that I want to classify, and based on that I will decide what is the label that I will assign to x. So if I start from this point and try to look what is the element that are closest to x, this is the closest element to x, and the label for x will be consequently minus, right? In this other example, if we consider k equal 2, what we will have is that we will find what are the two elements that are closest to this guy, and these are two guys. So in this case, I will not be able to determine what is the final label to x because I have a tie. I have the same number of elements with the minus label and the plus label. So that is why we don't use these type of numbers. So for k equal 3, which is a popular choice in KNN, then we will find the three closer elements to x, and in that case we will find this one, and this one. And based on that information, x will be assigned to the majority label in this dataset, which is in this case plus, and plus is present 2 times, and minus is only present 1 time, so plus is winning. So x will be assigned to the plus sign. This is how KNN works. What is important to remember from the k nearest neighbor is that we don't consider what is the information about the distribution of the data, right? We don't know that, and we don't use that information about the distribution. We discover what is the distribution when we decide on the number of neighbors that we want to use, and we classify based on that observation, right? So the distribution, which is the statistical parameter that I'm trying to explain here, is only estimated based on that observation. Another important thing to remember from instance-based classification is that they are called also memory-based because they classify by memorizing your training set. So you decide that you will classify based on a labeled data set that you have in place, and the way KNN will work will be based on the memorization of the entire data set. So given an instance that you want to classify using KNN, what you do is to use that training dataset, which is completely loaded in memory, to determine what are the nearest neighbors, and from that to classify your new dataset, right? Another feature that you need to know about KNN is that they are called lazy classifiers. Lazy because they don't train anything. There is no fit process involved in KNN. They simply work with the entire dataset loaded into memory, and there is no training per se, right? So in that case, KNN is limited to the volume of the dataset that you can work with in the memory of your computer. So if your dataset is huge and you need a very fast performance, then KNN is not the most appropriate method to be used. So remember that KNN is called lazy for that. There is less processing, but there is a lot of work to be done at classification time. So there is no training, but you need to work whenever you want to classify because you will have to compute a lot of things that we will see in a minute. If you have a problem which is very easy to be solved, like the one on the left, then the linear regression is perfect. But if the decision boundary that is separating small dots from the triangles here in the picture, that looks like this, what type of classifier do you use in this case? This is a type of situation where you need to work. KNN is a very good choice for this type of task. KNN and support vector machines, as we will see. What are the distance similarity functions that we will work with? We will work with Euclidean distance for the rest of the week, but I'd like that you will experiment with some of other distance similarity functions. And this slide is simply to illustrate how many different choices you have when it comes to the distance similarity, or how to determine that what are the closer or the nearest neighbors to your sample, to your event that you want to classify. The first thing you need to know is what is a distance. So the distance definition is important because you must comply with this definition to be used in KNN, and this is what it is. A distance function that takes 2 points and returns an scalar measuring how different those points are must comply with this set of requirements, okay? First one is that the distance between 2 points must always be non-negative. The distance between 2 points that are the same instance is always 0, symmetric if you want. And finally, the distance between x and y and z has to be always greater than the distance between the first element and the last element. So based on that definition, is this distance that I define here a valid distance metric? If you think for a moment on this fulfills all the criteria that I'm using, but this is not a valid distance metric because it does not provide any information about the events that I want to classify, right? These are some examples of distance measures. As I said, we will stick with Euclidean distance, which is the most popular one, the one that you remember from the high school probably, which is defined by the square root of the difference between each pair of elements in the dimensional space squared. Euclidean distance is the by default distance used in KNN implementations that you will find, but you have many other alternatives. For example, Manhattan distance, which is the one used in grids. For example, if you have blocks like this, and you need to measure the distance between this point and this point, the shortest distance can never be determined by the straight line between them both. You need to go like this, and this is why Manhattan distance is used in this type of situations. Another important distance is Minkowski, which is a generalization of all the distance above, given this parameter p. We will see in a minute how that behaves. If you have not mixable, mixable means that it does not make sense to add a random fraction of one dataset to a random fraction of a different dataset. Like, for example, it happens in on-time series. So in that case, the things that we use are dot products or correlation between all the events. These are not very much used because time series is probably not very much used with KNN, but it's good for you to know. For categorical variables, that is a very familiar example in our datasets, we use Hamming distance or Jacquard distance. Hamming distance is the number of, I will set an example. If I have the string A, B, C, D, and I want to compare it to the string A, D, C, E, I need to modify this one into this one and this one into this one. So the Hamming distance between them both is 2. Jacquard distance is another popular metric. I invite you to investigate a little bit on your own. Jacquard distance is basically measuring between two set of values what is the number of elements that they have in common divided by the number of elements in total that they have if you perform the union operation between the elements in A and B, right? So this is giving you a hint of what is in common between them both from the whole set of possible features that they could have in common. So Jacquard distance is extensively used and is very useful or helpful in categorical features. And these slides try to illustrate what is how do they behave. For example, this is Manhattan distance compared to Euclidean distance between the point A and C, stepping through B, right? So in Euclidean distance, the shortest path between A and C is always a straight line between them in an Euclidean space. But in Manhattan distance, the shortest path is always like this, right? And this is coming from this expression here. Minkowski is based on the idea that I can generalize this expression using the formula that you saw on the previous slide. And with different values of p, you obtain the different unit vectors that you can see here. If you're curious about this, try to research on what is the unit vector and what, for example, for this case, which is the typical case in the Euclidean space, what are the effect of changing that value. If you browse through the rest of the material up to the implementation of the KNN, probably you will get a better idea on how KNN works. And I will try to come up with some examples of how to build our own vanilla KNN version in Python, simply for the sake of illustrating how simple this method is and how powerful it can be. Thanks.